Jonathan Mattingly, who's going to talk about SPDE scaling limit of a Markov chain Montecarlo algorithm.
So thank you, David. Thank you, everyone, for coming, and to the organizers for inviting me to give this talk. So the reason I decided to talk about this is not because maybe it's the sexiest math necessarily, and not because so I should actually start off by, before I say the next thing, I should say that this is joint work with Natesh and Andrew Stewart and me, and that's somehow in descending order of how qualified they are to talk about this, probably. So, but nonetheless, you're stuck with me. So the good thing about that is that it will necessarily keep this elementary. So what I want to talk to you about is some work that we've done, extending work of Gareth Roberts, who should be listed here. So extending work of Gareth Roberts, who had some very nice insight into the following question. So one of the reasons also I want to tell you about this is that I think it's an interesting problem for this community, which maybe is not discussed as much or is not known about as much. So it's Markov chain Monte Carlo. So you have some density that you want to sample from, and you're gonna run a Markov chain algorithm, which I'll describe in a second, which will eventually, as time goes on, give you a draw from that distribution, or approximately a draw from that distribution. And you're interested in kind of studying its mixing rates. How long should you run that algorithm to get a nice draw? And in particular, what we're interested in is studying a phrase that you've probably heard a lot, or especially if you go to Bayesian statistics talks, it would be the curse of dimensionality. So we're interested in understanding a little bit about how this algorithm behaves as the dimension grows. Okay? So let me start off with, by the way, can everyone see if I write over here? Or is this? I guess that. Okay, so let me, so we're going to run a simple random walk Markov chain Monte Carlo algorithm. And that works as follows. So we start at a point. So we have some initial point. Let's call it x naught. And we're going to create a sequence x1, x2, x3, x4 as we run this Markov chain algorithm. And the algorithm goes as follows. First, we draw a y based on our current position, so based on xn. And that will be there'll be some distribution xn, some probability distribution, some transition. And then we're going to accept this proposal. So this is called the proposal. We're drawing a random variable y based on where we are now. So that's the Markov chain. And then we're going to accept this. So in other words, we're going to set xn plus 1 equal to y with some probability, and xn with another probability, so that they total up to 1. So this will be with some probability, which I'll call alpha x. What do I call it? Alpha y xn. And then, of course, this is 1 minus alpha, the same thing. And you just iterate this. And now there's a choice of what the right choice of alpha is. And I'll describe that in a second. So this is the algorithm. And so in the background, so what does this algorithm do? In the background, we have some density. We have some probability density. So we're interested in sampling from some density, f of x, x in Rn, for instance. And we want to sample, so this is some dx, okay? And we want to sample from this probability density. And we're going to use this algorithm with an appropriately chosen alpha and an appropriately chosen y, gives you an algorithm for sampling this. And what we're going to set up is a sequence of these problems. And I'm going to ask, how does this problem behave as n goes to infinity? Okay, is there some sense that we can understand how we should adjust things in this problem to somehow? Y is random. Yeah. So yeah. When I say draw, I'm always thinking of a a random draw, but yeah, it's a good question. Okay. All right. Okay. So let me. So what did Roberts et al. Do? And his co-authors around 97 and much after that. So what they had the nice insight. So they say, let's take our f of x, our f. So I'm going to make a sequence of problems. So I'm going to have an f of n. So I'm going to have a sequence of problems based on n-dimensional space. And these will be a product I equals 1 to n of f of xi. Right? So in other words, I'm drawing from a, so this is a density. So I want to draw my target density is product measure. So in other words, this is kind of a toy problem, right? I want to understand, I want to draw from this product measure distribution, but where each coordinate is independent and identically distributed with density f. All right, so now.
Does y depend on n?
Does y? It depends. It's a Markov chain. So I draw it based on xn with some distribution given by q. Okay? You should not have the full algorithm yet. I haven't told it to you. You will presently. Okay? So let me go ahead and say what that is now. So what we're going to do is we're going to, in this case, let's set y equal to xn plus some square root of delta rho, where rho is distributed normal, 0, and just the identity. So it's just IID normals, and we're doing, this is a random walk, right? I'm sitting at some point. I add a Gaussian random vector in some direction, which I've scaled by delta. And then I get a new proposal. And what is alpha? So alpha in this random walk case will always be alpha xy, for the moment, is always 1 min pi, and I always get them inverted. It should be obvious which one it is. I think it's, did I get it backwards? That's right, OK. What?
What's pi?
Pi, OK, I'll tell you, yeah. So right, so good choice, good question. So pi here, so let me, sorry, thank you. So yeah, I have my notes.
This is L.
Yeah, so it, so I want to draw from this distribution, and here's my rejection probability, which just comes what? Yeah, but not if I'm doing this. Not if I'm doing this choice. It's symmetric. So in this particular case, I have a simplification, which is good enough for what I want to talk about right now. All right, so I have this choice, and I'm taking this random walk step. And the question is, how do I want to scale this delta so that I somehow optimize the rate at which I converge to this density? Okay? And it's a simple calculation, which I'm not going to do, but I claim that if I use this algorithm, the invariant measure of this algorithm is, in fact, this distribution. Okay? And so that's what the random walk refers to the fact that I'm using this proposal. And the Markov chain Monte Carlo algorithm is just that I'm running this Markov chain. And this is Metropolis Hastings, which means I'm using this kind of rejection scheme. All right, so now, what did Roberts and all do, which is the nice observation? What they said was, well, if I think of this sequence, so what am I going to get out of this? I have x0, x1, x2. So if I think about this sequence and I want to embed it as a continuous process, so I can write down the linear interpolant, which is just what you think it is. So I'm just doing linear interpolation. So if this looks confusing, So actually, I apologize. I should have done this. I'm going to make, drat. Yeah, well, let's just try to, I'm going to try to change. I was using superscripts, but that's my own fault. Let me see if I can bother to do this correctly. So with n points, the kth one, this will be an interpolant between k plus 1 and k plus 1 minus nt xk, and this is for t in the interval k plus 1. Okay, so if we build this linear interpolant, then what Roberts and al. Showed is that Zn, I have to tell you something. So if we choose, so if we set delta equal to 2L squared over lambda n, which I'll describe in a second, what those constants are. If I do that, then in fact, so this is the n that I've already shown you. This is these are scaling parameters, which I'll describe in a second. And what this converges to, so if we set this, so now we let this depend on our problem, which problem we have, and we let n go to infinity. So Zn converges weakly to Z as n goes to infinity, where Z solves the following SDE. So I should be a little bit careful here. So somebody should have objected, and I'm surprised no one has yet. Here I'm in Rn. So which coordinate do I mean here? Right? This is a vector. So in other words, if I look at the ith coordinate of this, this converges to, so if I look at any coordinate, I pick the ith coordinate and I look at it, it converges to the following SDE. And then, what should I have here? I should have log f of z, derivative of that, plus square root of 2 lambda squared h of L dw. And as usual, I forgot my dt. And h of L is simply equal to, what's the constant? 2L squared phi of minus L over square root of 2. Where phi is the normal CDF. Okay? So that's interesting in its own right. So in other words, if I essentially, what I'm doing is I'm doing kind of a invariance principle argument in some sense. So we have this random walk with this algorithm, and it's converging to this solution of this SD weakly, okay, on C0t of R. Martin has. No. I have to have a drift, right? I mean, this is the SDE that has as invariant measure f. Right, so how could I have no drift? No, because I have to have a drift. Did I forget to scale time? Well, oh, right. NT. Where am I? Oh. Yeah, sorry. Yeah. Yeah, okay, sorry. Yeah, sorry. Yes, thank you. Of course. I did forget to scale time. Yes, good. Thank you, everyone. Good. It takes a community to write a paper. All right, so, or to give a talk, it seems. All right, so, but what's particularly interesting about this, right, is you immediately recognize that this, with this scaling here, by Brownian scaling, this is just a time change, right? So in other words, so lambda squared HL is just a time change. So in other words, if you maximize this, you will get this to converge faster. right? So it'll run at a faster clock. So if you want to improve the convergence rate, you want to maximize this function, right? So the question is, how do you maximize that? And that was one of the nice insights. Along with this, one of the nice insights of Roberts et al. Was that this is maximized. So h of L is maximized when alpha, when this acceptance probability is approximately 0.234. So what that means, so from a practical point of view, is that means you can run this algorithm if you were trying to sample from this distribution and tune your acceptance rate, because you can watch how many times you accept and how many times you don't. Tune your acceptance rate, and then asymptotically, as n goes to infinity, you'll actually be getting the optimal convergence rate. Okay, so that kind of tells you how the problem scales and how this curse of dimensionality comes in. It kind of, from this, you get an understanding of how time scales and how the acceptance rate should scale, okay? Which is very interesting, of course. Is that clear? Right, so I should say the average. So the average, so when, I mean, yes, it is, but it's a random variable, right? On a given step, as time goes on, if this is a random variable, right? And it will have some law of large number behavior, and you scale it to behave like this. Does that make sense? Perfect. Wonderful question. And yet another wonderful question, please.
What's the initial condition?
I smell blood. Yes, what?
So the initial condition for
What's the initial condition? So in this case, so the finer points, yes, thinking off. So in this case, for this theorem, the initial condition x naught is actually distributed as f. Okay? And so maybe you say, okay, well, how does that have to do with accept mixing rate? And you're a little bit correct there, but what this definitely has true is that if you were to look at xn, I think it's xk plus 1 minus xk, the square. Is that right? Yes, I think it's right. It maximizes this. Maximizes this at this choice. So in other words, it's taking kind of the biggest steps. Yeah, that's right. Of course, because if you make this if you say, well, you just make delta very big and it makes this very large, but then your acceptance rate goes to 0. Is that right, Andrew, with the square there? Yeah. Right. He said yes. I was just making sure I had the square right, because it's not in my notes. It's from memory. But then, of course, your acceptance rate is going to 0, and so you don't move very often, right? Yeah.
So in front of the Brownian motion, how can you have that complicated expression h of L? I mean, in the case when f is 0, right? I mean 1, then you just always accept.
Well, but you need an invariant measure. You need an invariant measure. I'm assuming you have an invariant probability measure. I mean, if your case is degenerate, right? Then it's just Brownian motion. I have
but
to.
if it's constant on, still, I mean, if it's constant on a piece, then when you scale with the delta n, you won't see the non-constant bits, right? So you would.
I don't know. I have to think about that. I mean, this is right when I wrote.
There is an answer to that. I mean, f has to be a density, and lambda is its variance. And if you have
Right.
this continuous density in the way Martin says.
Yeah, I didn't tell you what lambda was, actually. He's right. Lambda is this. Yeah, lambda is its variance. Yeah, I didn't write that.
Also, lambda isn't.
Lambda is not. Lambda is the integral of f prime over f dx, right? Or squared. There's something here that I should have written. Okay. Now you're happier? Maybe. It's always your friends. All right. So. All right. So, okay. So what? So why are you not happy? I mean, this is kind of interesting, right? It gives you a quantitative understanding of what they mean by the curse of dimensionality. So first I'm going to explain to you that, now I'm going to tell you what we did. So what we did was we said, okay, that's all nice, but this is product measure. That seems a little artificial. And why does this have anything to do with anything? Right? So what I'm going to tell you now is that we can prove a similar result for a non-product measure case under certain assumptions. And what will the limit be? So this was a coordinate by coordinate limit, right? I looked at the ith coordinate. Now what will the limit be? Come on, everyone, you know what conference you're at? It'll be an SPDE. All right, so instead, we're going to get an SPDE out in the end. All right, and the boring news, the momentarily tragic news, was it'll look exactly the same, and it'll have exactly the same acceptance-rejection result. So we have nothing new to tell the practitioners. And then at the end, I'll tell you why, of course, you knew that was the answer. And invoking the talks, the tradition started this morning, I'll recall my lecture here in January. And I'm joking, but I'm not joking. I'll tell you why my lecture in January is pertinent to what I'm saying today. All right. So, whoops, that's the wrong page. Where's 3? Here's 3. OK, so now to say everything I want to say now is I have to set up a sequence of problems. So I'm going to work backwards in some sense. I want you to think about, so I'm going to have a sequence of phi n of x, where phi n of x is equal to phi of Pn of x, where x is going to live in some Hilbert space. Just think of it as, you know, one-sided infinite sequences, if you want, with the standard inner product. Some Hilbert space, and pi n is going to be a projection. So this is going to be a summation k equals 1 to n lambda, let's call this j, lambda j, phi j, and then x phi j. So it's projection onto some basis phi j with some coefficients lambda j. And, oops, I don't want the lambdas there. What world am I on? OK. So let me write that now that I have space. OK, so now if I'm going to take this limit, right, if I'm going to have this limit have any stability as I go to infinity, right, I really don't want to work relative to Lebesgue measure. So I'm going to work relative to some background Gaussian measure on this space, and that's what the phi j's are. So the phi j's are my, so I'm going to say I have, so this is going to be a covariance operator for a Gaussian measure, which I'm going to call pi 0, and such that C phi j equals lambda j squared phi j. Okay, so those are the, so this is some Gaussian measure. These are its orthonormal eigenbasis, and these are its eigenvalues, all right? And there will be some assumptions, but I'm not going to belabor them yet. I promise to belabor them at the end. All right, and now, so this is my function, and my measures, my fn's, if you will. I'm going to write as the Gibbs measure. So these are, there's some normalizing constant, mn, which depends on phi, of course. And I should have said what phi was. Phi is my primitive function, which is from h into r. And the measure, my target measures, will be of the form phi n x. Okay, so now I'm thinking about this as a measure on my Hilbert space, but it's really only has finite dimensional support, right, in some sense, okay? Or alternatively, you can think about this as a measure, which is really the right thing to do. I should not say it the way I think about it, this way, okay? So it's a measure on R, where I'm just ignoring the remaining coordinates, okay? And now what I want to do is I'm going to set up this algorithm in the exact same way. So I'm going to now do exactly the same algorithm. And now let me tell you what alpha is. So alpha alpha, so let me just step back for a second. Let me say this correctly. So what I'm going to do is I'm going to say that y is equal to xk, the proposal, and it's going to be exactly the same thing, except now I'm going to say L squared over n, and I'm going to ck, where ck I are normal 0, 1. Normal 0, 1. So then, of course, this now becomes Gaussian, like this is distributed as my base measure. Okay? And I'm thinking about x naught be distributed as pi naught. Okay? And now, if I do the exact same linear interpolation, except not, and now if I take the limit of this, what do I end up with? It's right there. So now, under this setup, Zn converges weakly, and this is what Nitesh, Andrew, and myself proved. This converges weakly to the solution to this SDE. So as if in C0T H, this converges weakly to this SDE. HL Z plus C lambda, C Cauchy derivative of Z, and that's dt, plus square root of 2 HL. So we've scaled things slightly differently to get rid of some factors and have everything normalized correctly, but it's the same result. Same result. Okay, so now what happens? Okay, so this converges weakly to this PD, to the solution of this SPD. Okay, where H is the same H as before. That's the result. That's the big reveal, da-da. But now what I want to do is I want to, and of course this result, so formally at least, it's rather clear by the same calculations as before if you do them, that the invariant measure of this is this. The invariant measure of this is the limit of these invariant measures, which is some other normalizing constant. Well, so now what do I mean by this anyway? Actually, so somebody else should have objected. This is d pi 0 x, right? So in other words, this is the radon-Nikodym derivative of this with respect to this. And now if I take if I take n to infinity, this converges to some new normalizing constant, e to the psi x d pi 0. All right, so I claim that f is the invariant measure for z. And that was more carefully written down in some papers of Andrews and Martins and Logan's. All right, so good. So is this clear? So what's maybe slightly surprising, so what do I want to say now for the remainder of the time that I have? I want to tell you two things. So the two things that are maybe surprising, depending on where you come to this from, is how in the world does this Markov chain Monte Carlo algorithm end up producing this SPDE as its scaling limit? I want to give you some idea of where that calculation comes from. It's actually all elementary, which unfortunately what elementary means is irritating calculations that anyone could do, but no one wants to. And I want to tell you why is the answer the same. Why is the answer the same as the product measure? Okay, now there's been some assumptions. This is not true for any function psi, right? There have to be some restrictions on the function psi. And therein lies the devil. The devil is in those details. So I want to tell you those two facts. So maybe before I lose everyone delving into the calculation, I'm going to do a call an audible and change the order of what I was going to do. Sorry, it's a non-American, not a single American football fan in the audience, except maybe Tacos. So he spent enough time at Texas. It's inconceivable that he wasn't. So let me explain to you where this comes from. So let me actually give you the honest assumptions. So the honest assumptions are the following. So I'm going to, these are the core ones. There's some small other things, but these are the basic ones. So the basic ones are that I need, I want to make sure that my Gaussian measure is well behaved. So I'm going to assume that this is true. So there are positive constants, finite constants, so that this is true for some k greater than a half. Okay, so this says something about the decay of these eigenvalues.
Lambda k.
Yes, lambda j. K is here. But you were right to wonder. Okay, so now, and for some s in, we have the following. Okay, so this, so the value here is bounded above and below. So first of it's bounded from below, period. And it has quadratic growth. Okay. Has quadratic growth. Its Frechet derivative in the minus s norm is bounded. Of course, at infinity has to have linear growth. And lastly, it's Hessian, bounded as an operator from hs to h minus s is just bounded. Okay, and this is for some s here. Okay, so the fact that I'm doing quadratic only is not a big deal. I mean, you could work harder and do something else, right? If you had some other Lyapunov function estimate. We didn't write it down, but I have utmost confidence in that. The fact, this makes things nice and globally Lipschitz and has various other things, I think, and that can all go away. The part which is more important is this. Right? I chose this to not be such a bad perturbation. Right? I chose this to have nice continuity properties in a space which is not so bad relative to my structure, my Gaussian measure. And this actually is when I invoke my talk from January. Okay, so for those of you who weren't here or alternatively didn't commit to memory everything I said, and I had to look back and remind myself what I said, but I had the advantage of the notes. So the talk in February was kind of about what it means to be elliptic in infinite dimensions for an SPD. And in a way, what I was saying was that ellipticity, in a way, I was thinking about, well, okay, there's many things you could ask for. Which properties of being elliptic do you want to take to the limit? What I was saying is that there was a natural linear problem, a natural Gaussian measure in the background, which came from the problem. And when you added this nonlinearity, it didn't mess that up. It stayed absolutely continuous with respect to the underlying base measure. Okay? And the point is that this choice here does exactly that. So in other words, okay, there's a little bit of a problem here because without this smoothing operator, but we could put the smoothing back in the Q. But regardless, the idea is that well, actually, it's still true. The measure with this here doesn't mess up the tail, the asymptotic properties. When I go to higher and higher dimensions, anything that's true, it's absolutely continuous with respect to this problem. Okay, so in other words, so what I'm trying to say is if I mark this out, this problem and this problem are supported on the same set of solutions. It's just the relative weight changes. It's just just the Radinican derivative changes. So what that means is that almost sure properties as n goes to infinity, where n is, if I think about projecting onto larger and larger finite dimensional projections, as I take n infinity, those almost sure properties are, well, they're almost sure properties. Any asymptotic convergence rate, any kind of decay rate, those are all true. So what that means is that at infinity, it's dominated by the product case. Okay, so in some sense, the fix is in I rigged the game to work out, but I don't completely stand by that statement, that dismissal of what this says, because in a lot of cases, when you're thinking about a sequence of problems going to infinity, there usually is some stabilizing problem in the background. If you really wanted to think about if really asking about in what sense does this behave as the dimension goes to infinity, if there's not some stabilizing problem in the background, then it's a little hard to make sense of that. Yeah? And so at least in this case, you actually see. So in a way, this should not be surprising to anyone in the room, because this really is an SPD intuition, right? But it is surprising to some, when I show this to some, my Bayesian colleagues at Duke. And some of them were a little surprised that the rate was the same. That it didn't depend on psi, essentially. That the Roberts prescription for choosing the optimal rejection rate was the same.
It's very much dependent on the fact that also your proposal has a C1/2, which is exactly the covariant. So in some sense, it rescales things in such a way that in the limit, in the high coordinates.
Yeah. But of course, if I deviated from that, I would start having singular densities, one with respect to the other, and then everything would go to hell, and I would have no limiting problem, right? Right. So I mean, in some sense, if I want this to have a stable answer, this is my choice, right? I mean, there's also other choices. I could do Mala. I could do something else. I could do metropolized Langevin or something like that, and I'd have different answers. But you could Roberts work that out, and I see no reason why. Well, it'll be a little different here, but it would be so. Okay. All right. So this is where I transition now to explain to people why this algorithm gives this SPD. So if you want to hear ask about something else, you should ask now, because that will certainly fill the remaining 11 minutes.
So there, the drift had a nice interpretation. Here, with SPDE, what interpretation does the drift have?
A really nice interpretation. So I think it depends what you mean by nice. By nice, I think what you meant is that I took, so let's see, if I take the log of this density, well, that goes away, and then I differentiate, I get the same thing. The only thing that's different is this term, which is just the add-on due to the Gaussian. The Gaussian measure, right? It's like here I wrote it all with respect to, Roberts and company wrote it all with respect to Lebesgue. So if I wanted to shift so that I was writing this with respect to Gaussian, I'd be adding a drift exactly like this back in, right? Because that's the Redan-Nikkinen, that's the derivative of the density you would add to turn it back into a Gaussian, to make it write everything relative to a Gaussian. So this is the Fouché derivative of the log of the drift, right? I mean, the log of the density, written relative to the Gaussian. And that's what the relative to the Gaussian gives that term. Is that cool?
Yeah.
And then preconditioned by the C, as Martin said, to stabilize it. Okay, so what's the strategy of the proof? So the strategy of proof is a bit different than what Roberts and all did. And that's one reason why this was nice and easy for us, is that we thought a little bit differently about how to do it, and so it made it easier. Okay? So the first thing is you go, aha, it's additive noise, right? So they pass via kind of abstract Kurtz and Ether and Kurtz type martingale forms. Can you wait till the end? Is it on what I'm saying now, or is it back to where we were? Well, ask me at the end. Yeah. Okay. So the first thing to say is it's additive noise. So the Ito map, right, that takes a W and maps it to the integral to Z of t, right? Just written as the drift dt plus W of t. Right? So by this I mean this is a map to C 0 t is nice and continuous, right? Since it's additive noise. So that makes life much simpler. So what you'd like to say now, so for instance in particular, that means that if I have some approximate Wiener process that's converging like a nice polygonal interpolant that's converging to the Wiener process, that tells me it's very easy, cheap and easy to have then that Wn right? So if I have this, then I get that because of this nice continuity properties, right? It's a nice continuous map. All right, so that's the first point. And now the next point is, so then what we have to do, so now what we're going to do is I'm going to actually identify, so I'm going to identify W. And let me warn you right now, there's an epsilon lie in what I've written right now. We're not going to quite do that down in front. All right, so let me go ahead and tell you. So let's see. So we're going to define the mean at order n to be the function, which is this is our candidate mean, and our candidate covariance is, so the kth coordinate of this is some matrix, right? And its kth coordinate is, oops, no, I don't want to do it that way, sorry. The kth coordinate, the kth coordinate is square root of n 2l squared beta, which I haven't defined what beta is, but you'll have to live with that for a second. K plus 1 minus xk minus the expected W. Okay, so it's a correctly scaled, so beta is a constant, which I will maybe define in a second. Okay. So this is our candidate mean, this is our candidate variance, and so the calculation goes like this. So what we do, so the W there, although I haven't, there's a small lie, which I will reveal in just a second, is, here's our square root of delta t, so I'm going to set delta t just to help with the meaning of everything, is that, and that's going to be the sum of L equals 0, 1, and so that's just the first k steps, and then, oops, this should be n, no, this should be k. Say what everything is, and then there's just the linear, the minus the simple linear part. And t n. So that's just the linear interpolant. So that's just taking these steps, which have been correctly scaled, and those are going to be approximately little mean zero Gaussians, we'll show, with the right covariance. And so just by some kind of standard central limit theorem, standard kind of invariance principle, we'll be able to show that this converges to a Brownian motion. All right? And then if that's true, then if we look at xk plus 1 equal to xk, that's just equal to, of course. So I've written, this is at this level, this is an equality. So if I just condition on xk, that's what this conditioning means. Xk plus 1 minus xk plus the square root of 2l beta squared over n, just undo the scaling, kn. So that's an equality. And now the work is now to show that this is approximately L squared beta over n, mn xk plus the same thing. All right, so the first thing to show is that this mean, that this actual mean is approximated well by this function, which I wrote down somewhere, which I wrote down here. Good. Right? Because now, let's see what that says. So that says that this actual step, this is an equality, is well approximated by this for large n. And this, if you believe that this has the right mean and variance, is in a way an Euler approximation of this SPD. Right? So this is an Euler approximation. This is essentially an Euler approximation of the SPD. Okay? So then it would start to become believable if, in particular, I showed you that so first of all, by construction, you'll see that that this is equal to 0, and then we have to ask about the covariance. And we'll see that this goes to the right identity. Okay? So this will go, so we'll see this and we'll see that, and then that will say this is essentially an Euler step. Now, the small, nice technical trick is that instead of actually doing exactly this interpolant, we'll actually look at something which is a little bit different. Plus some error. All right, plus some error. And we'll choose that. So we will build this so that actually phi, the exact same Ito map, where did my Ito map go? The exact same Ito map of W hat n is actually equal to the process Z. So in fact, if I take the exact same Ito map, right, what do? The true map doesn't have the discretized version of this like the Euler step would, but you add and subtract it in, and you put the error into the Wiener process that's driving it. This is kind of a standard trick. And then as you take the discretization to 0, that little correction term goes away, and so then you can stick with the same map. So in fact, we build a slightly different one so that we don't have to go through the process of dealing with the Euler's in discretization. All right, so I was delusional to think that I could actually show you where this calculation came from. So trapped, because I mean, I heard lots of talks about this stuff before Andrew tempted me to work on this, and it always seemed kind of mysterious where this drift just pops out. How does that happen, right? I mean, I always implore everyone to give me the back of the envelope calculation, how the Euler step comes out of this rejection scheme. And unfortunately, the answer is just very simple in a way. But when I tell you that this is the answer without all the other background, you're going to find it very unsatisfying. But I'm going to give you this. Here's the answer. The answer is the following. There are two answers. So let C be normal 0, 1. Then it's a calculation that the expectation of 1 min e to the ac plus b, where these are constants, is a e to the a squared over 2 plus b phi okay, this is true. And the expected value of E, so if I let ZL be distributed normal minus L to L, then this is true. ZL, the indicator function ZL, is equal to beta over 2, where beta is just, it's phi evaluated something which I didn't write down. Okay, I think it's minus L over, I think it's this. But again, that's from memory. So, question mark here. All right, so that sounds a little unsatisfying, but well, let's just think for 1 second. Well, actually for about 45 seconds. What's happening here? What does this look like? The expected value of a step. What is it? It is, well, it's this random variable step right here. So we're doing the same step here. It's this step. It's this Metropolis Hastings step times the probability of actually taking it. Because the difference between now and the next step is 0 if I don't take it. So the expected value is just the expected value of this multiplied by the probability of taking that step. Okay, so what is that? Well, when I do that, the probability of taking that step. So when I take the expected value of this, I get, when I plug it all in there, I get some value, and then I have the rejection probability, which is 1 min, something that ends up looking like this. All right, so then you do this calculation, you get this answer. And now you'll have to take my word for it that A has a factor of 1 over n in it. So as A gets very large, this thing converges to, this is the CDF of a normal, converges to an indicator function. And as this converges to an indicator function, you invoke this. Okay, and so you end up getting out. And so then there's a prefactor that came out, which pops this part out exactly, which I don't have time to show you. But you know, it really comes down to just following your nose and then using these two calculations, which are not immediately obvious. Once I show you these, I have faith in everyone in this room that knowing that you're supposed to end up using these two calculations and using the fact that this converges to the indicator function. Oh, sorry, this is indicator function on this random variable less than 0, typo. That's what you do. Okay, so you're not supposed to be able to follow that. If I had time, I would have shown you more, but I'm over time now. So, but that's all you need to calculate it, and it just comes out of that. So the take-home message is, you know, the contribution here maybe was coming from the SPDE point of view, where we kind of knew that in a lot of situations where you set things up stably, the asymptotics as dimension grew would actually be dictated by the Gaussian, underlying Gaussian process. And so then you get this, what's surprising to some people, result that you should tune it in exactly the same way you would with the product measure for a whole lot of these problems. Now, of course, this is maybe baloney, because this is just asymptotic as n goes to infinity. And it's quite, you know, you can argue that by the time, you know, this is like saying that SPDEs, the asymptotic convergence rates kind of, for certain types of convergence, only depend on the local quadratic variation approximation. But of course, there are lots of examples where you never get close to that threshold. So it's maybe not as relevant, but it's an opening shot against the bow. And I think kind of continuing limits of these algorithms that lead to SPDEs has a lot of interesting problems for this community. And if you want to have more, be happy to send you to Andrew afterwards to talk to.
Thank you. We've just about got time for a brief question with a brief answer.
I cleverly ran over so that I boxed you out.
Lots of time for tea. Thank you for your talk and your patience.